We know the Myerson's characterization result now, and we also know what is the type of mechanism which are truthful in single object allocation domain. Let us now look at some of the examples of such mechanisms which are truthful and false in this class. So the first two examples are quite standard. So constant allocation and dictatorial, we know that those are monotone allocations, but they are not super interesting because they are very trivial mechanisms. The first interesting mechanism is that of second price auction. We have already seen it in various contexts. Let us see why it is falling in the same class, and how we can actually pictorially represent the second price auction in the context of Myerson. So let us look at the payment formula in this case. So we know that the first part is let's say it is assumed to be equal to 0. Then the second price auction, we know that this is not a randomized allocation, it's a deterministic allocation. You give the object to the highest valued agent. If that agent is a highest valued, then it gets this object with probability 1, and all other agents get it with probability 0, and it pays the second highest bid. So let us look at that agent which has the highest value in this case. So so imagine agent I is the highest valued agent. Then this function is nothing but a step function. We already have seen this diagram before, that this is the allocation. So this is the fi of ti t minus I, and where I is the highest valued agent, so its ti value is the highest. So we can look at the second highest value and denote that with t minus I2. So this is the max over all the other agents' valuations of their types. So as long as it's the type of agent I is below this value, it is not going to win that object, and after that it is going to win that object with probability 1, and exactly at that point the allocation can be anything. So there could be multiple agents who can be probabilistically given this object. That will not have any impact in terms of the payment that it makes. So you can look at this. So this is going to be exactly 1 for player 1. So this is going to be ti. So essentially this is nothing but this whole rectangle here. Now if you look at this quantity here, this is nothing but this green shaded region. So if you subtract that out, payment is nothing but this red part here, and therefore the utility is this the ti, which is nothing but the whole area of this rectangle, minus that payment, which is coming back again to this blue green part here. So as we can see that the payment is just this part, which is nothing but the 1. So what is this area under this red region? It is the second highest bit multiplied by 1. So therefore this is the second highest bit. So we know that this payment is nothing but the second highest bit. So this is the second price auction, and it can be very well classified inside this Myerson class of mechanisms with the appropriate values of fi and ti. Now let us look at the efficient allocation with a reserve price. So we have seen this earlier, that the second price auction, in the second price auction, on top of asking the agent for the second highest bid as their payment, one can also set a reserve price and fix something like a maximum value of t minus I2 and that reserve price I. So what happens in that case is this threshold gets replaced by the max of these two quantities, t minus I2 and that reserve price here. And there also we can see that the allocation rule is monotone, and therefore the corresponding payment will be just this point, so max of these two things. And the argument is exactly similar to the second price auction, so we will not go over it once again. So this efficient allocation with a reserve price is also a non-decreasing allocation rule, and therefore you can design this Myerson mechanism which will be truthful. But now let us look at some not so common allocation rules. These are something which we haven't seen before, and unless we knew the Myerson's mechanism or the Myerson's characterization, perhaps we would not have thought about this kind of rules to be truthful. So suppose the allocation has three components. The first component is whether to decide that if that object is to be sold at all or not. So A0 is the decision where it is not sold. A1 is the decision where it is sold to agent 1, and A2 is it is sold to player 2, and there are only two players in this case. So now, given the type profile T1, T2, the seller first computes this corresponding number, which is a maximum between three numbers. So the first thing is some arbitrary constant, let's say 2, and the second and third are T1 square, so the type of player 1 squared, and T2 the type of player 2 cubed. And it will select A0, A1 or A2 depending on which of this is the maximum. So if this is this maximum, so if this turns out to be the maximum, then the mechanism will not sell this object at all. If this happens to be the maximum, then it will give the object to player 1, and in this case it is going to give it to agent 2. This is a very strange mechanism, but what we are going to argue is that here also this mechanism, this allocation rule is monotone, and therefore you can design the corresponding the payment formula, which will make sure that this mechanism is implementable in dominant strategies. So why is this monotone? So you can see that you can break the tie in whichever order, and suppose there exists already a tie-breaking rule. So the player 1 will get this object if its T1 crosses this threshold of max of 2 times T2 square T2 cube. So essentially square root of that. So if this happens, so it is essentially spelling out the condition under which this becomes the maximum. So if that becomes the maximum, then player 1 will get that object. So it will have a very similar allocation function. It will also be a step function, and this threshold will be given by different numbers, something like this. This is for player 1. If this threshold becomes this, then it will, after that it will start getting that object. Before that it will not get that object. Similarly, for player 2 will get this object where this threshold is being replaced by this. So this will, then that will be the allocation rule for player 2. Actually, this should be T1 and this should be T2. So there is no T3 anywhere. Okay, so that's the condition. So what we can see is this allocation rule for both these players is a monotone allocation rule, and therefore we can equivalently compute the corresponding payments using the Myerson's formula, and we can make this mechanism dominant strategy incentive compatible. Okay, so let us now look at the property of individual rationality. We have seen this property earlier, but in the context of single object allocation, this will have certain implications on the Myerson's result that we have shown in the previous module. So the mechanism is ex post individually rational, and we emphasize this term ex post, which means that even after all the agents have revealed their types, participating is weakly preferred. So this is the meaning of ex post, even after all agents have revealed their types. So even after observing everyone else's type, it will be beneficial for you to participate. So the definition is fairly simple. Your expected utility is going to be non-negative for every type of your own and the types of the other players, and this should hold for every player. So what are the implications of individual rationality on the Myerson's characterization result that we have seen? So here is the lemma, which says that formally. So a single object allocation, in the single object allocation setting, if we have a DSIC mechanism f comma p, then it is going to be individually rational if and only if this the constant that we had in that integral formula is going to be non-positive. And on top of that, if you also want to ensure no subsidy condition, then this pi tit minus I has to be non-negative for all these players. Then this constant quantity is going to be exactly equal to 0. So this is nothing but the condition of no subsidy. That is the payment given by each of these players has to be non-negative. Then this quantity has to be exactly equal to 0. So let us look at why this is true, and in fact the proof is really very simple and straightforward. Because this is individually rational, we already know that this mechanism is DSIC, so we can, without loss of generality, assume that the Myerson's payment formula holds. And the payment formula, so because we will have to ensure that this is going to be non-negative for every valuation. So what is the definition of individual rationality? This inequality should hold for every Ti and T minus I. And we know this from the Myerson's result, the payment formula that we have to satisfy. We just replace those values with Ti to be equal to 0. So then the first part actually goes away. It is going to be 0. And also those two integral parts. So Pi Ti T minus I had the first term was just the 0 and T minus I. But the second part has Ti Fi Ti T minus I. This also goes to 0 when you plug in Ti to be equal to 0, and integral from 0 to Ti f of x T minus I dx, that will also go to 0 if we plug Ti to be equal to 0. So essentially in this part there will be only this term left, and because it has to be non-negative, we have this Pi has to be non-positive. Pi 0 of T minus I has to be non-positive. So conversely, if we have this to be non-positive, then we'll have to show that this also satisfies the individual rationality constraint, and we can do that just by writing down the utility expression explicitly. We have this Ti f Ti T minus I, and then expand out the payment formula as we have here. We notice that these two terms get cancelled out. And now this quantity is nothing but this is a probability distribution, so therefore all these terms will be non-negative, and we are taking the integral, so this part will be non-negative as well. And because this term is this Pi 0 is non-positive, so negative of that will be non-negative, so the whole term will be non-negative as well. So therefore we have proved that this mechanism with this condition of on Pi 0 is going to be individually rational. Okay, so in part 2 we are going to prove on top of individual rationality, we also want to ensure no subsidy. So all the payments has to be non-negative, and if that has to happen for all TIs, you can as well put that Ti to be equal to 0, and that has non-negativity now. And by individual rationality, you already know that this has to be non-positive, so the only possibility is that this is exactly equal to 0. So and the converse thing is always true, that if we have this to be exactly equal to 0, then it is very straightforward to see that this is going to be individually rational by the very condition that this is exactly equal to 0. And it is also not going to be not going to have any no subsidy condition, because it is not going to give any subsidy because of the fact that the allocation policy is monotone. So we can again draw something like that, the picture that we have shown last time. The payment is always going to be non-negative. Okay, so that's with that, let us now go into some mechanisms which are non-Vickrey auctions. So so far we have discussed only Vickrey auctions, that you have a threshold and only one agent who is crossing that threshold is the sole winner. So this is something like a mechanism which is a deterministic mechanism, but our characterization result of Myerson does not only apply to deterministic mechanisms, it also applies to non-deterministic or randomized mechanisms. So let us look at some of those examples, some randomized mechanisms which is also truthful under this setting of single object allocation. And we are going to focus mostly on budget balance, that is the payment that has been made by all the players. If we take their sum, that should be very close to zero, if not exactly equal to zero. Okay, so the first mechanism that we are going to define is that the object goes to the highest bidder. Again, this is a deterministic mechanism, but the payment is such that everyone is compensated some amount. Here also the allocation is very straightforward. The highest bidder gets the whole object, and all the other agents get zero allocation. So their payment, if you look at the Myerson's formula, only the constant term remains, everything else goes away. So but for player 1 there is something which is left over, so we'll calculate that. So let us assume that in this mechanism those constant values are decided in the following way. The constant value for player 1 and that for player 2 is nothing but minus 1/nth of the third highest bid. So without loss of generality, we are assuming that this T1 to so T1 is greater than T2, T2 is greater than T3, and so on. They are ordered in a decreasing order of their types. Now everyone else, apart from this highest and the second highest bidder, receives 1/nth of the second highest bid. So which means that this is going to be Ti 0, T minus I, that is going to be minus 1/n of the second highest in the rest of the set. Tj, J is not equal to I. So in this case, this is just going to be T2 because that's the second highest bid. Okay, so now we can use that constant things, and the fact that because this is dominant strategy incentive compatible, the Myerson's payment formula will hold. First thing to notice that this kind of a mechanism is a monotone allocation rule. So you are always giving it to the highest bidder. So the highest bidder, the threshold when it crosses the threshold of the second highest bid, it is going to be the winner. Before that, it is zero, and therefore this is a monotone allocation rule. So the payment, so this is that constant part. So P0, P1 0, comma T minus 1. This is this is that expression which we have already defined. Now the player 1 is going to be the winner, so therefore this is T1 multiplied by 1, and the last term of that integral formula is integral from 0 to T1 f1 x comma T minus 1 dx, and this player does not win until T2, so therefore this integral will be nothing but T1 minus T2. After T2 it starts winning with probability 1, and therefore when you sum all of them up, T1 cancels out from both sides, from here and here, and what we are left with is this. So similarly, player 2 pays just this amount because the rest of the part is 0 because it does not get that object. All the other agents are getting minus 1/n times T2. So this is according to the definition. Now if you look at the sum of all these payments, you can do this calculation. There will be n minus 2 all other agents. What you will have is 2/n times T2 minus T3. And as n increases, you can see that this excess amount of money that is going to be taken away by the auctioneer goes very much close to 0. So this is a deterministic mechanism that also redistributes the money, but it redistributes ensuring that this is truthful. Let us look at a non-deterministic mechanism, a randomized mechanism, which allocates the object with probability 1 minus 1/n to the highest bidder, and with probability 1/n to the second highest bidder. So this is also a monotone allocation rule. You can convince yourself. So what is this constants? So constant is nothing but minus 1/n. We can pick the constants in whichever way we want. This mechanism picks it as minus 1/n times the second highest bid in the rest of the agents, right? So for instance, this will be T3 for player 1, this will be T2 T3 for both player 1 and player 2, and T2 for all the other players. So we can do this calculation. So we can see that so when player 1, so again we are assuming that the type of player 1 is the highest, and it keeps on decreasing with increasing index of these players. So the first constant is, so this is the P0, the constant of this integral, and so with probability this the player becomes the winner. So this is T1 times F1, and F1 is nothing but 1 minus 1 by n, and then we have the integral. So this entire part is the integral from 0 to T1 F1 of x comma t minus 1 dx. Now we know that between 0 to T3 the player does not win. From T3 to T2, this is the second highest bidder, so therefore it has a probability of winning, which is 1 by n, so between T2 and T3. And from T2 onwards to T1, this is the highest bidder, so it will have this probability of winning, which is 1 minus 1 by n. This is between T1 and T2. So if you do the integral, divide the integral into these parts, you will get this all these terms, and if you sum them up, you will get this quantity here. Similarly, you can compute the second highest bidder. Second highest bidder will only have up to this point. Here it is not winning, here it is winning with probability 1 by n. And when you take the sum, you will see that this is going to be exactly equal to 0. And for all other players, the payment is going to be just the constant quantity, because they never win. So the only constant quantity is their payment, and because this is negative, it means that they are getting paid. So player 1 is actually paying, player 2 is paying nothing, even though it is getting some share of this allocation. All the other players are not getting anything, but they are getting some payment, so they are being compensated with some payment. But the interesting thing is, now if you sum all these payments together, it will be exactly equal to 0. So this mechanism is certainly this mechanism is certainly strategy proof because of the property that we have used. This is falling in the Myerson's class. The allocation is monotone, and the payment is following this payment formula. But additionally, it is also ensuring budget balance. What it is losing because of this allocation rule, it is not efficient. And we have seen this before. The allocation, if that becomes efficient, then it is not going to be budget balanced, which is the problem with VCG. That problem persists even in this situation. We have found a mechanism which is redistributing the money. So someone is paying and someone is getting paid, and the allocation is such that this is monotone, and it is strategy proof, but it is not efficient, yet it is budget balance. So since our objective is budget balance, we have seen a mechanism which is budget balance and also falls in the Myerson's class.